Gracias a todos por conectarse a esta nueva edición del Seminario de Investigación del MANEMAT. Voy a cambiar a inglés. Thank you for joining us. This session, we have the talk of Timm Treskatis. Timm is a very good friend of us, mine specifically, a really nice mathematician, applied mathematician, who is very in close contact with us during these years. He's working in complex fluid simulation. Today, he's going to talk about Elastoviscoplastic fluid flows, which is a relatively new field, right? There's very interesting problems there. And it's very nice for me to have Timm to discuss this, because I know that Timm is very creative in this approach. So I'm really excited to listen to this talk. Timm, thank you for accepting the invitation. Sorry for the change in dates. You know that sometimes this things happens, but now welcome to our seminar, and well, the audience, the Zoom audience is yours, Timm.
Thank you very much, Sergio, and thank you everyone for coming along to this talk. It's great to hear that so many of you want to learn the thing or two about elastoviscoplastic fluids and constitutive equations that are actually integral equations. This is a project that we mathematicians, Stefan and I, are collaborating with some colleagues from the German Research Center in Aerospace and Aviation with Sebastian and Thomas, and they are both physicists. And so as always, when you work in an interdisciplinary team, it's a bit challenging at first to find a common language and to understand what both of us can contribute and how we can get along with each other. And this is a particularly applied problem because the physicists, they are interested in some kind of glass melts and other polymer melts that are elastic, viscous, and plastic at the same time, so elastoviscoplastic fluids. And they really want to get a physical understanding of these things, while we are then confronted with the challenge of modeling these flows and finding ways of simulating them numerically. And because I personally find glass melts pretty complicated fluids that probably most of us don't encounter in our everyday lives, I thought I'd start with another elastoviscoplastic fluid, which is a lot more common in a bread country like Germany here, some dough. So what does elastoviscoplastic mean? If you are working with dough, you would notice that if you stir, it's pretty hard to stir, but you can stir it, even though it's harder than just stirring your cup of tea or coffee. So it certainly is a fluid which has a viscosity. It also has some plasticity, because here you can see that someone has poked this dough maybe with some fingers, and then there is this little hole in the dough, and it doesn't bounce back, but it stays in there, and this irreversible deformation, that is a characteristic property of plasticity. And in particular, when you knead it for a long time, and you knead it and you knead it, you notice that it actually becomes more and more elastic over time, because it bounces back like a spring, at least to a certain extent, if you poke it. So dough would be one typical example that is viscous, elastic, plastic, all at the same time. And if you work with it as a baker, you just get a phenomenological understanding of all of these properties. For physicists like our collaborators, these observations of these phenomena are not really enough, because they would rather like to understand, why does dough or glass melts, why do these fluids behave that way? Why do they have these material properties? So they really want to look at the molecular structures and how the different molecules interact with each other to understand why that macroscopic behavior comes from these microscopic interactions. And the answer, the explanation here in case of the dough would be that wheat flour and many other flours contain gluten, that protein, and if you start kneading the dough and knead it over a course of time, the gluten are long protein molecules which will form networks in the dough that eventually behave like an elastic spring, and that's why the longer you knead the dough, the more and more elasticity you will observe. And this is like the physical understanding that our colleagues really want to get, explaining macroscopic behavior like elasticity, plasticity, viscosity from molecular behavior of these fluids. So here we have just a little sketch of these two scales. Maybe if you have worked with rheology previously, you know these typical sketches that some models for fluids, for complex fluids, they often contain combinations of a viscous dashpot, which has a characteristic viscosity, an elastic spring with a spring constant, and then some plastic friction element, where you need to overcome a certain minimum stress, the yield stress tau naught, to break it until that moves freely. And yeah, all of these things are like very heuristic explanations, or not really explanations, observations, but our objective really is to model the microscopic behavior and the polymers like the gluten molecules and how they interact to get an explanation for macroscopic behavior like that. If you look at the literature of what kind of models there are for viscoelastic or elastoviscoplastic fluid flows, then you can often find various combinations of these macroscopic viscous dashpots, elastic springs, plastic friction elements. For example, if you want to model viscoelasticity, you can combine the spring and the dashpot either in parallel or in series, and then you either get the Kelvin-Voigt model for viscoelastic solids or the Maxwell model for viscoelastic fluids. Then you can combine the two and have viscosity and elasticity in series, but then another viscosity which is always present, and that gives you the Oldroyd or Oldroyd-B model for viscoelastic fluids. And then if you want to add plasticity, you have various ways of adding that element in there, and you can just make it arbitrarily complicated. So there are many more or less heuristic models that try to refine and get a better fit on parameters. But like I said, our objective is to not really take these approaches that try to get a macroscopic fit to observations, but to get a microscopic model and then derive macroscopic behavior from that. In the end, we still want to be able to link the two. So I'm just briefly going to show you some of the typical models and how we can phrase them as mathematical models. So for example, here for the Maxwell or Oldroyd-B model in viscoelasticity, what we need is, of course, a momentum equation for the velocity u that appears here. That's just a typical Navier-Stokes equation where we have possibly from a solvent, that maybe water, that our polymers are dissolved in. We have the background viscosity of the solvent, which is always present in the equation, but then possibly some additional viscoelastic stress, which has its own constitutive law in the form of a differential equation. I'm going to say a few more words about that in a moment. Like for this talk, I'm just going to look at incompressible fluids. So we just assume that the velocity field is always divergence free. And I know that many of you are working with Newtonian and viscoplastic fluids. I'm not sure how familiar you are already with elasticity and this upper convected derivative that appears in this equation here. So I'm just going to say a few words about that so that we're all on the same page and know what kind of equation we are dealing with. I'm sure you're all familiar with the Lagrangian frame of reference that just traces a little fluid volume with the flow, and then the Eulerian frame of reference, if we just look at it from the outside. And we have these relationships for changing frames of references between the two. For example, if we look at the scalar quantities such as the density or a mass concentration, then if we want to know how does the density change in that little fluid volume that I'm following here with the flow, then the total rate of change in the Lagrangian frame of reference, if I just follow that little volume of fluid along its streamline, that may have just an instantaneous rate of change because it's actually changing, so the total density is changing, and then it may also change because it's actually moving to a different place where there may be a different density. So these are the two contributions that we have for scalar, also for vector valued quantities. And here we have our equation for changing from the Lagrangian frame of reference to the Eulerian frame of reference. If we are looking at tensor valued quantities, such as the stress, which is a tensor, then we do actually have to include some additional terms here. And that is simply due to the fact that if we're measuring the stress, then we also have to look at the deformation or any rotations that our volume of fluid undergoes. So of course, if I take a little cube and then I stretch it, that will cause some additional stresses in that little fluid volume. And that is why then, if we do again that transfer from the Lagrangian frame of reference to the Eulerian frame of reference, we do get these extra terms that include velocity gradients, which measure the deformation of our little fluid element. Otherwise, just think of that upper convective derivative as the total time derivative in the Lagrangian frame of reference that is moving with the flow. So going back to our constitutive equation here, we effectively just have an ordinary differential equation for the stress, and in the simplest case, that decay constant lambda is just the ODE for exponential decay, where the steady state would be, again, stress is equal to the typical Newtonian behavior with the polymer and additional polymer viscosity. But over the course of time, we have exponential growth or exponential decay with the time scale lambda towards this Newtonian steady state. And that would be the Maxwell or Oldroyd-B model of viscoelasticity. Later on, we'll look at some other models where the lambda here can also depend on the strain rate again, and then we also get plasticity in these equations, and these are then generalizations which are no longer called the Maxwell or Oldroyd-B model, but then these are White-Metzner models. Okay, going to microscopic descriptions, which would then come from statistical physics, which describes interactions between different polymer molecules and how we can describe those. We still need a momentum equation, and this is basically the same as before, except that now we have a stress that will be given from a different constitutive equation that is somehow based on statistical physics. And these relationships from statistical physics, they usually need the deformation of the fluid. So not just the rate of deformation, that strain rate, but the actual absolute deformation. And one way of measuring the deformation of a fluid is given by the finger tensor, which is here called B. What is the idea here? Again, if we start measuring the deformation beginning with just a little cube of our fluid, then we can say that cube is spanned by the unit vector in x direction, the unit vector in y direction, and the unit vector in z direction. And all of these vectors combined into one 3x3 matrix would be the identity matrix. So that gives us the default configuration. And then if that little volume of fluid is again deformed, rotated, etc., our little vectors that span the deformed cube, they would also change. And now that we know about this upper convective derivative, we can deduce that to get the finger tensor, the exact deformation at any later time, starting with the default configuration at a reference time t prime, we just have to solve this streamline ordinary differential equation, or otherwise it's in the Eulerian frame of reference, an advection reaction equation to get the deformation at a later stage. And then we have a different or rotated x vector, y vector, z vector that spans the deformed volume. And the reason why we're solving that with an equal to 0 on the right-hand side is, again, if you think about what's actually going on in the Lagrangian frame of reference. So imagine you're trapped inside this little fluid volume, and then that is being deformed. if your entire world around you that you live in is being deformed with you, you wouldn't actually realize any change, and you just see that in your Lagrangian frame of reference, there is no change. But then only when you look at it from the outside and you do that transformation with the upper convective derivative, you would actually see that deformation. And that is why we can solve for the deformation tensor by solving this advection reaction equation for later times. Okay, that's our second equation, and then we get some equation from statistical physics that gives us the stress in here. The term that we are integrating here, the rate of change of the deformation, that is also sometimes called gamma dot here, because we have the deformation as our variable. I've just kept it that way. And the G, that is the Hookean constant, or the modulus of elasticity, which gives us the relationship between deformation and stress. So that's basically like the proportionality constant, but it doesn't necessarily have to be proportional, but it can be highly nonlinear. So in general, for some very complicated models, the constant in here that links the strain rate to the stress, it could depend on our current time, it could depend on the reference time in the past, and then possibly also on the entire history of deformation that our fluid has undergone, like all the way back to Adam and Eve. You can see that here we are integrating really all the way up to the current time, but then starting from all the way back and from the first days of the universe, and all of this history could possibly enter such an equation. And the G, that function here, that is where the actual physics happens. So then we would have to ask the physicists what their model is for the G that we can then plug into the equation to find the stress macroscopically. And the last equation, just like before, is that we are still looking at incompressible fluids. I briefly mentioned before that the objective of our colleagues from physics is to solve microscopic models with a G that comes from statistical physics, and then get macroscopic behavior that we can observe. And in fact, you can often find special G's that just simplify this integral equation to something that is a differential equation, like for Maxwell fluids or even a Newtonian. For example, if you just say that, well, if our viscoelastic fluid, our polymers, have some memory, then it might make sense to assume that the memory fades exponentially in time. So of course, things that have happened only very recently, they probably have a stronger impact on the flow than things that happened hours or years ago. And just using some exponential decay might probably be the simplest assumption. And the way we can incorporate that into a model that's not statistical physics, that's really just a simple idea, is that we have a G that does not actually depend on the T prime and the entire deformation history separately, but we really just say the G is exponential decay with time scale lambda, and the further we go back in time, the more that memory of the fluid has decayed, the less weight the strain rate will have in this integral. And I'm not going to do the calculations, but you can just sub it in and use the Leibniz integral formula to show that this will actually reduce this integral model to the differential model of the Oldroyd-B or Maxwell model. So two ways of thinking about the Maxwell model, either just having an elastic spring and a viscous dashpot, or thinking about it as polymer molecules that have a memory which decays exponentially in time. Both of these are equivalent descriptions of the Maxwell model. How can we solve such equations that are given in integral form numerically? Well, they're difficult to solve. And one big challenge that we have comes exactly from that integral, because not only do we have the velocity that we have to solve for and the pressure at each time step, and maybe some additional stress variable like we do have for the classical differential models. But now we also have the entire deformation history, like the deformation at the current time, then the deformation from some past time, and we have to take snapshots, ideally, well, continuously, all the way back to time t prime negative infinity that we have to keep in memory. And even if we discretize that, we still have maybe 25, 50, 100, 200 of these B tensors for different reference time t prime when we started measuring deformation. So you can see this is actually a huge system of equations that we have when we have this integral over the history variable t prime. That's massive. As a result, we do, of course, have to save degrees of freedom for our discretization wherever possible. And there is no way we can solve 3D problems at the moment because that is just way too much memory and CPU requirements, but we're going to focus on 2D problems. And what I'm using here for the discretization is really the lowest order approximation that we can possibly use. I really just want to use piecewise constant approximations for the deformation tensors, piecewise constant for that weighted sum after we discretize the integral for the stress, also piecewise constant for the pressure, and then a piecewise linear approximation for our velocity fields to make sure that everything works fine and that this is LBB stable, etc. All the other assumptions we need for a reasonable approximation. I'm using these BDM elements of order 1. So like I said, piecewise linear. But then if we look across elements, the normal components of the velocity, they always remain continuous, and only the tangential component of the velocity may jump as we cross a triangle edge going from one triangle to a neighboring triangle. So the normal velocity remains continuous, tangential component may jump, and that means that we have to use some discontinuous Galerkin techniques. But not only, the only benefit of this approximation is not only that we have relatively few degrees of freedom, in particular for this entire array of deformation tensors, but it has a number of other advantages that our colleagues in physics do care about. So first of all, this approximation, you can show that it's well known. This is LBB stable. It is also an exactly divergence-free approximation. That means the incompressibility constraint, divergence of the velocity is 0. That is actually exactly satisfied by such an approximation. As a result, our solutions will always be exactly mass conservative, and physicists, as they really care about conservation laws, this is the best we can get because mass is really conserved even after discretization in every single point. At least if we look at balances of momentum over each triangle, we also get the conservation law satisfied there for each little control volume. This discretization has a property which is called pressure robustness. That's also a very desirable property, in particular if you have the momentum equation with some right-hand side, because it means that your discretization will recognize what part of the right-hand side will only change the pressure and what part will also change your velocity. If you come from a numerical analysis background, pressure robustness means that your error estimate for the velocity will not depend on the pressure error, but is really just dependent on the velocity error. And this is a very desirable property. The only thing we have to be really careful about is, like I said, because we may have tangential jumps in our discrete velocity. This is not a conforming, not a H1 conforming approximation. Gradients are not generally in L2 if we compute it of our discrete velocity field, and that's where we have to use some discontinuous Galerkin techniques to make sure we get a consistent and stable approximation. Here, once again, these are our equations, and we can see that there is a velocity gradient hidden in here. Here, everything is fine. here we really have to be careful about, because our test functions in the weak formulation for this equation are velocity fields. The divergence is fine because our normal components remain continuous. We can, without any problems, compute the discrete divergence. That's fine, but we really have to be careful in the momentum equation and in this equation for our deformation fields that we get a proper discretization. So here, just a quick example. If we look at the ODE effectively, or the advection reaction equation for the B tensors, we have this advection term in here, and then if we find the weak formulation of this term, we have a test function also of the dimension of a deformation field with a contribution over all our triangles, and then an additional contribution where we integrate over our edges in the mesh. And there we then can introduce, because we can have jumps, after all, the B's are just piecewise constant, and then we would have a jump over each triangle edge. There we use an upwind flux for those to get a unique B over these edge integrals. We can do something very similar also for these advection terms in our momentum equation. And then, like I said, the tangential component of our velocity fields can jump, and that causes some issues potentially in the approximation of the divergence in here. Once again, if we integrate by parts, we get some contributions which are still standard, but also appear in continuous Galerkin finite element approximations over area integrals. And then we have additional terms that also include that we may have jumps in the velocity fields here, the test function that can jump in tangential direction, which gives us some additional terms with boundary integrals. And finally, the last thing is that we also have some penalty terms for the tangential jumps to make sure the entire formulation will be well posed at the discrete level with some positive penalty parameter in here. Okay, that's just a very quick overview. Some other challenges that we encounter when we are solving these things is that, well, the absolute deformation of a flow that never becomes steady, and it doesn't have an upper limit, because we're not looking at the deformation rate, but really the absolute deformation. Now, here's just an example. If we start looking at 2 points in our flow, here in a channel flow that are initially very close together, now the top one is moving more slowly than the bottom one, and as a result, they will move further and further apart. Well, if you want to think of it as a little control volume, that is getting stretched more and more, so that deformation really grows with no limit. And this can be particularly challenging if you are in an enclosed domain, like here, this is a sketch of a lid-driven cavity, where, again, these 2 points that are initially very close together, they are separated further and further, and theoretically, that deformation will grow without any upper bound and can really approach infinity. Whenever that causes any numerical issues, you can, instead of looking at the finger tensor B for the deformation fields, you can instead switch to the square root of that, which is another deformation tensor that's usually called E, and that can alleviate the issue, because after all, the square root doesn't grow as fast as the original deformation field, but it's not really a great fix, and sooner or later that may become numerically unstable too. At least it alleviates the issue. Another thing that requires some thought, even though after discretization, this will just be a weighted sum of all of these B fields that we have, it does pay to actually think about what are reasonable ways of where we discretize our integral. Shall we use something like a mesh with a constant grid spacing, or rather something like that? The other issue is that we can't actually, of course, go infinitely far back in time, but we have to make a cut somewhere. And I'm not going to go into any detail, but discretizing that integral is a big challenge, and there are many ways of doing it and many ways of doing it wrong, that it doesn't work. And the other thing is like, once we have discretized everything, how do we actually solve for all the unknowns in each time step? And I'm just going to give you a quick overview of what I'm doing. Like at each time step, we assume that we have a velocity field given. Then what we can do is we have all of our B tensors for the different T primes, and we can advect them one time step forward. Then we have all of these new B's, and we can discretize this integral, sum up with a weighted sum, all of these B tensors to get a stress. Then plugging in the stress into the momentum equation, we can solve these two equations in a coupled way to get a new velocity field and a new pressure field. We take that new velocity field, go back into the B equation, and do that at each iteration until this has converged. Finally, let's look at some results that we get from all of this procedure. And I think the first thing that is pretty interesting is how, if we are in a setting where we have an equivalent differential model and an integral model for the same problem, such as for Oldroyd-B fluids, then how do our computation times compare using either the differential model or the integral model? The benchmark problem here is the classical TU Dortmund benchmark example with a flow around a cylinder. And it doesn't look particularly unusual. This is just viscoelastic flow. And if we use the differential formulation of the Maxwell model, it took me about 1 minute on my laptop to get the steady state solution. If I use the equivalent integral model to solve the same problem, and now I take my T prime history axis and I take 25 snapshots on that axis to model the deformation history of the flow. That took more than half an hour already to solve for the same problem. And the solution is not particularly accurate. So if I increase that to 50 snapshots over the history time axis, I already need more than an hour to get something even more accurate with 100 snapshots and 100 finger tensors. That takes me more than 2 hours. So once again, 1 minute for the differential model, more than 2 hours to get exactly the same solution. The conclusion really is that whenever we have a differential model available, probably we want to use that. And we only want to use the more general integral model whenever that simplification is not available. Something else that I'd like to show you, because I know there are many people in your group that look at viscoplastic fluids, and we can actually get the Bingham model in this integral formulation if we make our relaxation parameter, that lambda, that time scale, strain rate dependent. So like before in the Maxwell model, the lambda was just constant, but if we use this, what is called a White-Metzner model, where the lambda now depends on some constant contribution plus another shear thinning, strain rate contribution, and then the total stress has a contribution with a background viscosity that will be shear thinning, and then an additional contribution with that elasticity, viscoelastic but shear thinning. That reduces to Bingham if we take the limit of this constant contribution to 0, because if we have a strain rate that approaches 0, then you can see that also 1 over that elastic timescale approaches 0, or vice versa. The elastic timescale approaches infinity, which means we get an infinite viscosity here, and that is what gives us viscoplastic Bingham behavior. Here are what the results look like, and again, using the integral model, theoretically, I have to integrate to time minus infinity. Realistically, I have to make a cut somewhere, and then it would depend on using my advective time scale of the flow. Do I just integrate backwards 1 advective time scale, or 5 advective time scales, or 10 advective time scales? And you see that the further backwards I go, the better the Bingham approximation becomes. And we really have to integrate a certain amount of time backwards in time until we see that plug flow that is characteristic for Bingham. In fact, the green line here that is visually indistinguishable from the analytical solution. But I think if you have followed Sergio or Sophia, you know that computing Bingham flow is difficult, and here, if we get it from the integral formulation, we see this difficulty from another perspective. Also, once again, if we in the ideal setting, the 1 over lambda c contribution for Bingham would be just 0, and we only have the other contribution. If we use that parameter as a regularization parameter, like we make it starting from 1, we make it smaller and smaller and smaller to approach the Bingham setting, then we see the very typical behavior that the closer we get to Bingham, the harder the problem is to solve, and the more fixed point iterations we need in a time step to get to Bingham, and it will increase further as we get to that singular limit. But that is very well known for Bingham, so not surprising that we also see it with the integral formulation. In summary, integral models for elastoviscoplastic fluids, they are complicated. We have seen that they need an insane amount of computation time, and even though I was able to show you convergent solutions in the end, it is not easy to get them, and I haven't shown you all my failures because, believe me, it is really hard to solve all of these coupled equations. On the positive side, even though we may not want to use them for Maxwell Oldroyd-B fluids where we have simpler differential models available, that G function in there that really opens up a whole universe of physical models that model microscopic phenomena. And our objective in the long term will be to use such complicated integral models, but also physical integral models to get an actual understanding of what is going on at the physical level, so that in a few years' time from now, we hopefully will have gained a better understanding of fluids such as glass melts, or maybe also bread dough, using molecular models from statistical physics. And that concludes my talk. Thank you.
Thank you very much, Tim, for this very interesting, very nice talk. And well, this time for questions. If someone has questions or comments, please, at the time.
Me.
Sophie, please.
Yeah, Tim, just maybe a very naive question about how do you actually solve, you have a really huge system with the integral model. Yeah, so maybe if you can tell us a little bit of how do you solve this very huge and nasty system that you have?
We can go back to the slide here. So these are my equations, and now just imagine that these have already been discretized in time. So then the time derivative here will have been split into just a difference quotient in time, also the time derivative here. And of course, ideally we would use something like a Newton method that uses higher order information, but with that big system, I believe it's just not feasible to solve everything in a coupled way. So effectively, I'm just using something like a Fecha iteration, and that's why I just assume that when I have my initial condition and then I want to get my first time step, I just assume I have my velocity field given, maybe constantly 0, and then I take my velocity field to get all of my 25, 50, or 100 B's, update those. I can use all my B's in this integral equations, which will then be some weighted average or weighted sum of all the B's after discretization to get my sigma. Here in this equation, I have always assumed so far that I have a solvent contribution, so that I do have something like a Laplacian as well in the sigma hidden, which is not shown here, but in all of the cases that I have done so far, we effectively have a Navier-Stokes problem with the sigma on the right-hand side because it's already known, and then we can just use a conventional Navier-Stokes or Zen linearization to get the U and the P, and with that updated U, we go back and go through that circle until convergence. And that's what we have to do in each time step. And that's also the reason why we get these insane computation times. The more B.
Yeah, okay, I get it. And just the second thing, you told us about this at the end of the talk, but what would be the advantage in the next years of this work? I mean, because you told us this, maybe in some years we can do really understand these kind of fluids, but like right now, what can you tell us about that?
The equation framework is pretty general. So the thing that is not determined yet here is the G function. And the example I showed you was basically where the G was given by a simple ordinary differential equation, maybe just a simple exponential decay or exponential decay with a time-dependent time scale. The interesting things start to happen when the G is a lot more complicated and really uses statistical physics, where, for example, our collaborators, they are looking into something called mode coupling theory. And with that mode coupling theory, the G is given as yet another system of integral differential equations that you have to solve using the T, using an independent time variable T prime, and then the entire deformation history. That would be an example of a model which does not reduce to a differential model anymore, but then you need this more general framework to actually solve these kind of problems, and they are really physical. So it's not just that you say, oh yeah, elastoviscoplastic means spring coupled with viscous dashpot and with some friction element, but then you really look at behavior of molecules and how polymers interact with each other. So that's physical laws from statistical physics that enter the problem and that we then can use in a flow simulation. It's really physical understanding instead of just some model that you use using some heuristics.
Okay, thank you so much, Tim.
Good questions. Thank you very much, Sophia.
Felipe, por favor.
Hi, Tim. Thank you for the great talk. I have a brief question about, you mentioned that you're using linear order finite elements, right? Mm-hmm. You mentioned also you're using that because of the computational cost.
Yes.
But did you have other issues using higher order, maybe oscillations? Because I know that discontinuous Galerkin had several issues. I don't know if you can tell us about your experience.
Exactly. So the challenge really is that you have to make sure that your fluxes on the edges are chosen appropriately, and then everything goes well. At least the BDM elements, they are not fully discontinuous, but at least the normal component of the velocity field remain continuous. That means we need fewer fluxes than for a fully discontinuous Galerkin method. But it seems like this is really a sweet spot where we have lots of advantages, that we can still have all of these very beneficial properties, and then the non-conforming issue is relatively small because we just have some tangential jumps that we need to penalize in our formulation, and we get these additional integrals. I'm using what is called a local discontinuous Galerkin approximation of second derivatives here. And then as long as the penalty parameter in this term, the kappa, is positive, everything is fine. You don't have to take any extra care. If you use an alternative approach, which is called the interior penalty or symmetric interior penalty method, then you always have to make sure that the kappa is not just positive, but it even has to be big enough to make sure everything is well posed. But with this local discontinuous Galerkin formulation, we have a few extra terms compared to the symmetric interior penalty method, but at least any positive value of the penalty parameter will give us a stable system. So that's one small advantage here. And that makes things a bit easier than with other DG methods, but it's right, because they are not conforming, whenever we have second derivatives, things get a wee bit tricky, but eventually I think the other benefits still outweigh that we have all of these nice physical properties plus still a very low order, because it's a very well-known property that, for example, P1, P0 with fully continuous Galerkin methods would not be stable for Stokes, Navier-Stokes problems, and then just giving up on the conformity and saying that we can have tangential jumps, that fixes everything and gives us all of these extras on top. So you're right, yep, it causes some difficulties, but we also get lots of benefits from it.
Great, thanks.
Thank you, Tim. I just have two questions. Probably I missed in the answer you gave to Sophia, but very simple questions. You implemented this in which
Phoenix.
language, or Phoenix?
Phoenix.
And so do you design some kind of an ad hoc algorithm for the solution? I mean, some kind of Newton or something like that, or just
It's a car method.
the bumps?
Yeah, for the system of equations here, it's really just starting with some initial guess and then iterating until convergence. So it's really just a simple fixed point method, because everything else is basically not feasible trying to linearize all of these equations. In particular, if you have 25 or 50 of these equations here, that would just get too much to solve everything at the same time.
Yeah, no, I'm just because the few I know about this EVP flows are that in some point in the classical differential models, for instance, the BMP and that, you almost any time you have to perform some kind of a fixed point iteration for the auxiliary questions, and that makes very slow and complicated the situation. And I think you have the same thing here, right? So, yeah. Okay. So I think there are a lot of things to do in that area also.
Oh yeah.
Thank you, Tim. Thank you. It's very interesting. I mean, I know that these fluids are kind of a trendy now. So guys, you have to think about it. Maybe we have to add a need to our BP community, probably. Felipe, you have one more question. Please go.
Yeah, sorry, just right now that you mentioned that you're using Phoenix, I'm wondering, like, you're able to compute the numerical fluxes, do the integrals around the elements using Phoenix?
Yep.
Is okay, so that's possible. Right. So,
yeah, what you have to do here is in Phoenix, you have these plus and minus operators where you can decide if you are on such an edge where two triangles meet. One of them will randomly be assigned the plus and the other one will be the minus element. It doesn't really matter which one you take because everything is fully symmetric. And then if you just have to take one normal vector. It doesn't matter whether you take the normal vector of the green triangle or the normal vector of the orange triangle. Both will be the same. So you really can just type this equation the way it is into Phoenix. You have just a plus that you can add to the tangential and the normal vectors. You have the average operator in Phoenix. You have the jump operator in Phoenix. And that is all you need. So effectively, as always in Phoenix or with U of L, when you have your weak formulation written down, it's almost the same in Phoenix. And the same also applies to these DG formulations.
Nice, thanks.
Okay, perfect. So, Tim, thank you again for the talk. Thank you for accepting the invitation and talk here. As always, guys, the video will be available soon in our webpage as soon as I can modify the webpage. I hope this week. The contact information of Tim it will be available. You can ask me. It's okay because I'm sure that we can. You wanted to ask questions or something like that. I don't know. For sure, I will contact you, Tim. So we have a future let's say events. I mean, we have the DMS, the conference, and so if someone want to add to this discussion about these complex fluids, hopefully we can create our own small community inside this big community, which is nice. Okay, thank you everyone for connecting today, and see you next week for the next edition of the seminar, and Tim will be in contact for sure. Thank you again.
Thank you, Tim. Nice to see you.
Bye.
Nice talk.
Bye-bye.
Bye.
Bye.